Hello and welcome to the Geometric channel. This video is part 2 of our lesson on trigonometry basics, where we will cover the sine and cosine ratios. If you haven't seen part 1 on the tangent ratio, you can check that video out right there. If you'd like a guided notes worksheet for this video, click on the link down in the description, print it off, and follow along with me. Now in part 1 we talked about how we can use the acute angles in a right triangle to tell us information about the lengths of the legs and vice versa. Specifically, we said that for any given acute angle measure, the length of the leg opposite of that angle over the length of the leg adjacent to that angle is a constant ratio. And we've come to know that as the tangent ratio. Now the fact is we can apply this idea of a constant ratio when we relate each leg to the hypotenuse of a right triangle as well. And this is where we get what we call the sine and the cosine ratios. So, with definitions here, the sine ratio, abbreviated SIN, the sine of angle A is equal to the length of the leg opposite of angle A over the length of the hypotenuse. So here's angle A, the length of the leg opposite of angle A, which would be this leg down here, opposite meaning on the other side of or not touching, over the length of the hypotenuse of the right triangle, hypotenuse being the longest side or the side that is opposite of the right angle. Okay, so that's the sine ratio, leg opposite of angle A over the hypotenuse. The cosine, abbreviated COS, of acute angle A is equal to the length of the leg adjacent of angle A, again over the hypotenuse of the right triangle. So angle A, the length of the leg adjacent to angle A, adjacent meaning next to or touching, that would be this length right here, over the length again of the hypotenuse. Okay, so those are your ratios for sine and cosine. Now if we put some numbers in here, we'll go with the 3, 4, 5 right triangle once again. So in a 3, 4, 5 right triangle, I want to write the ratios for the sine of angle A and the cosine of angle A. So the sine of angle A again is opposite leg. So here's A, opposite leg would be 4 over the length of the hypotenuse, longest side, which is 5. Okay, so the sine ratio for angle A is 4 over 5. The cosine ratio for A, cosine being adjacent over hypotenuse, adjacent to A would be 3, over the hypotenuse, which is again 5, 3/5 for cosine ratio of A. We can also take sine and cosine ratios for the other acute angle in the right triangle, that would be angle B. And we'll do cosine ratio for B as well. So angle B down here, sine ratio for B, what leg is opposite of angle B? Opposite goes straight across. That would be 3. Hypotenuse is still 5. And then cosine of B, the leg adjacent to B, is 4 over the hypotenuse, which is 5. Now notice that the sine of A is the same as the cosine of B, 4/5. Just like the cosine of A, 3/5, is the same as the sine B, 3/5. Now this is because these two angles, A and B, are complements of each other, or complementary to each other, meaning they have a sum of 90. We know that because in a right triangle we already have a right angle by definition, and if a triangle is a total of 180 degrees, take out the 90, we have 90 degrees left in between A and B, they have to be 90 degrees. In fact, the word cosine literally means complement of sine, cosine. Okay, algebraically, you can think of this as the sine of an angle is equal to the cosine of 90 minus that angle, which is one of the many trigonometric identities you'll learn as you study trigonometry. Now, we can use the sine and cosine ratios in the same way we used the tangent ratio in part 1 of this lesson. The difference now is it's up to us to decide which ratio is going to be best to use based on the information that we have. Now, a good way to remember your ratios is a mnemonic. I'm going to write it out here. The mnemonic is Sohcahtoa. Okay, kind of a weird little phrase here, but this is an easy way to remember what ratios you can use for each of these trig functions. Okay, so Sohcahtoa. S in this case stands for sine. C here stands for cosine. And T stands for tangent. Okay, so we've got the three ratios, sine, cosine, and tangent. And for each ratio, we have two sides that we use to relate to get the ratio that we want. So for sine, the ratio is the opposite leg of your angle over the hypotenuse. Okay, so sine ratio is opposite over hypotenuse. The cosine ratio is the adjacent leg over the hypotenuse. So cosine is adjacent over hypotenuse. And then tangent, the two legs, opposite leg over the adjacent leg. So if you can remember this mnemonic phrase here, Sohcahtoa, you'll know what your ratios are for each function. Okay, so I'm going to take this little mnemonic and I'm going to kind of write it up on the side so we have it there to use. So Sohcahtoa, keep that in mind. Let's just write it up here. Okay, so let's get some examples. Let's say we've got a right triangle with a 35-degree angle. We have a length of 20 across the bottom, and we're looking for this side right here, this hypotenuse. Okay, so when we're doing problems like this, we have all three ratios at our disposal. We could use sine, we could use cosine, we could use tangent. It just depends on what sides that we have in relation to our angle, which ratio is going to be the best one to use based on what we have here. So we're looking for the hypotenuse. We have this leg down here, which that is the leg that is adjacent to my 35-degree angle. If we look at the leg that's opposite of the 35, there's nothing here. It's not x, it's not anything that we know. So we can kind of ignore this side. Sometimes I find it helpful to label my sides as opposite, adjacent, and hypotenuse, which I'm going to do for each one of these examples here. So if 35 degrees is my angle that I'm using, opposite of that would be here, so I can just put a little O for opposite. My adjacent leg is down here, there's my 20 that I have, and then my hypotenuse is what I'm looking for, x. Okay, so the two important sides in this case are 20, the adjacent leg, because I know it, and then x, the hypotenuse, because that's what I'm trying to find. Now, to decide which ratio I'm going to use, all I have to do is find the ratio that relates the adjacent side to the hypotenuse. So if I look up here, which ratio relates the adjacent leg to the hypotenuse, A and H? I can see A and H right here. That's cosine. Okay, so cosine ratio is going to help me solve for x in this particular problem. How do I go about it? We start with our acute angle, which is 35. We're going to take the cosine ratio for a 35-degree angle. Okay, so cosine ratio, which again is the adjacent leg over the hypotenuse. So my cosine ratio adjacent leg 20 over the hypotenuse, which is what I'm missing. And there's my equation. Now, how do we solve this again? We've got the makings of a proportion. All we have to do is put this ratio of cosine 35 over 1. Again, that doesn't change the value of this number here. So cosine 35 over 1 equals 20 over x. And at this point, we're going to cross multiply to get our equation of 20 equals x times cosine 35. Okay, we got one more step to solve for x to get x by itself here. So we've got x times cosine 35. To get rid of this times cosine 35, I'm going to do the opposite, which is divide by cosine 35. Do that to both sides. That becomes 1. So I've got x equals 20 over cosine 35. So x equals 20 over cosine 35. This is where we would go to the calculator. Okay, again, check your mode, make sure you are in degrees. double check it real quick. We are in degrees. Okay, so again, I've got 20 divided by cosine 35. 20 divided by cosine 35. And we see our answer is, if we round, we're going to say about 24.4. 24.4. Now again, in problems like this, a lot of times you're going to have a problem in some type of context, whether it's a length or some type of measurement. Always check your labels and make sure you get your label on your answer. In this case, I didn't have a label, so I got 24.4. Now it's always helpful to check your answer with your problem or with your picture. Obviously my picture is not drawn to scale because I just drew it freehand, but I know that my hypotenuse does have to be the longest side of that right triangle. So my leg down here is 20 units long. I know that my hypotenuse is going to be longer. In fact, looks like it's just a little bit longer. So 24.4 seems like a reasonable answer for this type of problem. So it's always good to go back and check. Just kind of look at your picture, look at your situation, and see if your answer seems reasonable. In this case, that looks pretty reasonable. Okay, let's try another one. So right triangle here, we're going to go with a 62-degree angle. X here, and we'll say 65, we'll say feet, in this case, 65 feet. Okay, so first step again, if we kind of assess what we have and what we're looking at, first step is going to be, let's label these sides as opposite, adjacent, and hypotenuse. So remember, opposite and adjacent is always in relation to your acute angle. If you know the measures of both acute angles, which we kind of do, since we know that we've got a right triangle, if we know one acute angle, we can get the other acute angle. But we can pick either one. In this case, we've got the 62-degree angle there, so we're going to base our lengths opposite and adjacent off of that 62. So which length is opposite of the 62? Which leg? That's over here, so this is opposite. We've got an adjacent leg right here. And we've got hypotenuse right here. I'm going to switch my x, just because we did cosine last time. So let's say my x is here, switching it up. Okay, so my x is here, looking for this length. Hypotenuse is known at 65 feet. Okay, so if I decide which ratio I'm going to use based on the information I have, I'm looking at the two sides that either have a length or a length that I'm looking for. In this case, I'm looking for the opposite leg. I have the hypotenuse. The adjacent leg has nothing there, so I'm going to kind of ignore that side. So which ratio relates the opposite leg to the hypotenuse? Opposite hypotenuse, that's right here, that's sine. Okay, so we're going to use the sine ratio for this particular problem, based on the information I'm given in the picture. Again, setup is the same. I'm going to take the sine ratio for a 62-degree angle. So that looks like this, sine of 62 equals, and then my ratio is opposite over hypotenuse. So make sure I get them in the right order, opposite on top in the numerator, hypotenuse in the denominator. Opposite being x, hypotenuse being 65 feet. So there's my setup, got my ratio. I'm going to put sine 62 over 1 to get the proportion, and then I cross multiply to get x equals, and then 65 times sine 62. And at this point, this is where I go to my calculator. I'm going to type in 65 times sine 62. And we can see we've got we'll say 57.4. So x equals 57.4. Always check your rounding. Again, check your instructions, see what you're rounding to, and check your labels. This time we're in feet. So I've got 57.4 feet. Checking my answer with my picture. My hypotenuse is 65, so I know that's got to be the longest. Okay, this opposite leg, this is the longer leg, a little bit less than 65. That seems reasonable. So 57.4 feet. Let's do one more. Now again, often your problems for these types of problems could have some context, or could have a story problem or a word problem involved. This last one we're going to have a little context. So let's say you got an airplane, and the airplane is flying at an altitude of, we'll call it 12,000 feet. And the airplane's flying along, and the airplane wants to land there. And we'll say that he's about, we'll say 98,500 feet away from its landing spot. And we want to know what is the angle of depression that the airplane will have to land at to get to its landing spot. Okay, so I have kind of a lot going on here. The first thing we need to do is we need to make a right triangle. So I've got these lengths here. I'm going to go ahead and kind of connect and make this right triangle. Okay, so the angle of depression is what I'm looking for. I've got my right triangle. I've got this distance as 98,500. My altitude being 12,000 feet. I'm going to kind of move that over here. Okay, so I've got my right triangle here. This is what I'm looking at. Now notice this problem is a little different, not just because it's an airplane problem, but because now it's the angle that I'm looking for instead of one of the legs or one of the sides. Okay, I've got two lengths and I'm missing my angle. Okay, if you remember in the tangent video what we had to do with this particular type of problem, it's the same with sine and cosine, which we'll talk about in just a second. Let's go ahead and set it up. So my angle is what we're missing. I've got my two sides. I have to decide once again, what ratio am I going to use? So we'll start by labeling. Here's the hypotenuse. Here's my angle, so opposite of that angle is going to be here. Adjacent to that angle, the adjacent leg is here. There's nothing on the adjacent leg. So the two sides that matter here are opposite and hypotenuse. And if I look up at my mnemonic, which ratio relates opposite and hypotenuse, that's right there. So we're going to use sine once again. Okay, so using sine, set up my ratio as the sine of my angle. What's my angle in this case? I don't know, it's x. So we've got sine of x equals, sine ratio is opposite over hypotenuse. Opposite is 12,000 over the hypotenuse, which is 98,500. And again, when I was looking for the side, I would make this ratio, put that over 1 and cross multiply. If you're looking for the angle, not the route I go. So when the angle is what you're trying to find, we can't use the regular sine function. We have to use, again, what we call an inverse. If you look above your sine, cosine, and tangent buttons, you should see an inverse function, or a cosine -1, sine -1, tangent -1. You can see them right above there. Okay, so when you're looking for the angle, we have to use that inverse function. How does that work? What I want to do is I want to take the inverse sine of both sides of this equation. What that does is that kind of undoes itself, so sine inverse of a sine kind of cancels it out, and we're just left with x. Now when I take the sine inverse of this side, those cancel and I have x. When I take the sine inverse of this side, I have a function that I can type into the calculator. Okay, so here that's gone. I've got x equals, run out of space here, x equals, when I take the sine inverse of 12,000 over 98,500. Okay, and that's what I'm going to type into the calculator here. So to get to the inverse in this particular calculator, you hit second sine. You can see that little sine -1. Then I typed in my fraction of 12,000 divided by 98,500. Okay, when I type that in, am I off? I am off. That's the way it goes. Let's try that again. So sine inverse, second sine, 12,000 divided by 98,500. Okay, and we've got an angle that looks like it's just about 7 degrees. So we've got x equals, if I round, we're going to get about 7 degrees. So So a 7-degree angle of depression is what that plane will have to descend at to get to his landing spot over here. Alright, so there's so many applications of trigonometry that will span well beyond right triangles. But learning and understanding these 3 basic trig ratios of sine, cosine, and tangent will give you a real solid base to build from as you go. If this video was helpful for you, you can really help out this channel by giving it a thumbs up, and consider subscribing to this channel if you want to see more videos like this one. As always, thank you for watching.